have you ever stopped to think about all the invisible technology that's kind of humming away in the background of our lives?
Mm,
I mean, things like smart appliances, medical devices, even, the systems inside your car. They're all run by this hidden
right.
intelligence.
Often completely unseen.
Exactly. And these are what we call embedded systems. They
Yeah,
are absolutely everywhere.
they really are.
So today on the deep dive, our mission is to sort of pull back the curtain a bit. We're going to explore the fascinating and incredibly complex world of embedded software testing.
It's a big one.
Yeah, we've really dug into the material from Embedded Software Testing Explained to pull out the key stuff, hopefully giving you a shortcut to understanding what's really going on.
And it's so important to understand this
Yeah,
because, I mean, while these systems are meant to be invisible, their perfect operation is, well, it's non-negotiable.
right.
Think about critical applications like a pacemaker or maybe an aircraft control system. There's just zero margin for error. Safety, reliability,
Mm-hmm.
it all hinges on the testing.
Absolutely. So let's kick things off with the basics then. What exactly are these embedded systems?
Okay, so material defines them as electronically controlled devices where the software and the hardware are really tightly bound together. They work as one unit.
Ah, tightly coupled.
Exactly.
Mm.
They often have like specialized computers built into other equipment to do very specific jobs.
Mm-hmm.
And like you said, most of the time, we don't even realize they're there.
Hmm.
And that definition really shapes what embedded testing is all about. It's not
Mm.
just checking the code.
Right.
It's this whole process of looking at both functional and non-functional things for both the software and the hardware.
Both sides of the coin.
Yeah. The goal sounds simple, but it's incredibly challenging. Deliver a product with zero defects that does exactly what the client needs it to do.
And it feels like it goes beyond just, meeting a spec sheet. This kind of testing, it's fundamental for guaranteeing security, reliability in really vital areas.
Totally vital. We're talking medical devices, railway signals, aviation systems, the automotive industry.
Huge sectors.
Yeah. And it's not just about safety. This rigorous testing is also often mandatory for getting official software certifications. You have to do it.
Okay, that makes sense. So let's get into the why and the how then. Why is this testing so critical? The research points to a few key reasons, right?
It does. And they're especially powerful in the embedded world. First, obviously, is finding bugs.
The classic reason.
Right. But unlike, say, a phone app where you can push an update pretty easily,
Yeah, quick fix.
fixing a bug in a million cars or pacemakers already out there,
Yeah.
that's massively expensive, maybe even impossible. So finding bugs early is just exponentially more valuable here.
Okay, so early detection is paramount. What else?
Well, that leads straight to the second point, reducing risk. The stakes are just so much higher. For the users, obviously, but also for the companies making these things.
True. A bug isn't just an annoyance. It could be dangerous.
Yeah. Exactly. Catastrophic even. Third, doing this testing properly up front actually cuts down your overall development and maintenance costs later on. It's always cheaper to fix a bug early.
Makes sense. Find it before it gets baked in.
Precisely.
Yeah.
And the final reason is really about improving performance, making sure the system does what it's supposed to, exactly when it's supposed to, reliably.
Okay, so those are the whys. What about the how? What do the actual testing activities look like day to day?
It's quite a structured approach. You start by giving the software very specific inputs, carefully chosen inputs.
Okay.
Then you execute a particular piece of the software using those inputs. And then comes the really crucial bit.
Yeah.
You watch closely.
Observe.
Observe the software state.
Yeah.
Check the outputs. Does it match what you expected? Does it meet all the requirements? And critically, did the system crash or behave unexpectedly?
So you're really putting it through its paces.
Absolutely. Input by input under all sorts of conditions you can think of.
Given how complex these systems are, that sounds like a massive task. How do they structure it? The material mentioned 5 fundamental levels of testing.
That's right. It's not just one big test at the end. It's a layered approach, very methodical. Like building something complex, you check each part as you go.
Okay, break it down for us. What's the first level?
So first up is software unit testing.
Hmm.
This is really granular. You're testing just one function or maybe a small class module completely on its own.
In isolation.
Exactly. Usually the developer who wrote it or a teammate does this. Peer review is common. The tests are based just on that tiny module's specifications. Think of it like checking one single gear in a clockwork mechanism.
Got it. Smallest building block. What's next?
Next is integration testing. And this actually splits into 2 types. Software integrating with other software and then software integrating with the hardware.
Ah, okay.
Here you're looking at how different bits interact. How do the software components talk to each other? How does the software talk to, say, the sensors or actuators, the
Oh,
hardware
right.
parts?
The connections.
Yeah. And a unique challenge here, especially for embedded, is that the actual hardware it's going to run on is often being developed at the same time as the software.
Oh, wow. That sounds difficult.
It is. It makes testing everything perfectly in just a simulation really hard.
Yeah.
You often need to get onto the real hardware or something very close to it quite early on.
Okay, so unit, then integration. What's level 3?
Level 3 is system unit testing. Now, the unit you're testing is much bigger. It's a whole framework.
The whole framework.
Yeah, like a complete software code, the real-time operating system, the RTOS, which is crucial for timing, plus all the platform stuff like how it handles interrupts, tasks, communication,
Okay, so a much bigger piece of the puzzle.
a much bigger piece. And how you control and observe it changes too. Instead of just calling a function, you're often dealing with messages sent between different software tasks via the RTOS, like an internal messaging system.
Internal communication.
Right. Very important for systems that need instant reactions, like anti-lock brakes.
Yeah.
You also watch system resources memory, CPU usage. And gray box testing is common here.
Gray box.
It means you know something about the internal workings, but maybe not all the source code details. Responsibility for this level can vary a lot between different companies.
Interesting. Okay, level 4.
That's system integration testing. Now you're testing a set of components working together within a single node or device.
Like one computer box in a bigger network.
Sort of, yeah. Or one major subsystem. The way you interact with it, the points of control and observation becomes a mix. It might be network messages coming in or going out, or still some RTOS level events inside the node. You might even use a virtual tester to pretend to be another node in the system.
Getting more complex. And the final level.
Finally, we hit system validation testing. This is the top level. You're testing either a whole subsystem or maybe the entire embedded system end to end.
The whole enchilada.
Pretty much. The main goal here is proving that the system meets the requirements from the perspective of whatever it interacts with externally.
Like a user?
Could be a person, yeah. Or it could be another machine, like in a telecom network. It's the ultimate check. Does it do what we promised it would do in the real world?
Wow. That's a really thorough, layered process. So how does all this compare to, say, testing a website or a mobile app? What makes embedded testing so different?
That's a really key question. And the source material lays out some clear distinctions. First is the scope.
Yeah.
Standard software testing, it's just about the software. Embedded testing has to involve both the software and the hardware it's running on and controlling. You can't separate them.
Right, they're tied together.
Then there's the methodology. A huge chunk of regular software testing, maybe 90%, is manual black box testing.
Meaning you just use the interface like a normal user.
Exactly, you don't look inside. But with embedded systems, testing can be black box, sure, but it's also very often white box, where you do need to look at the internal code and structure.
Because the internal timing and logic are so critical.
Precisely. The focus areas are different too. Regular software testing often focuses on the GUI, the user experience, validating data, checking databases.
Yeah, making sure the buttons work and look right.
Right. Embedded testing. It's laser focused on the behavior of the hardware in response to inputs.
Yeah.
How does it react? Is it fast enough? Is it accurate?
Much more about the physical interaction.
Absolutely.
Yeah.
And finally, the application domains. Standard testing is your websites, your mobile apps, your business software. Embedded testing happens on the hardware itself, the microcontrollers, the medical machines, the systems in your car.
So that tight link, that unavoidable connection with the physical hardware, that's really the defining thing that makes embedded testing unique.
That's the heart of it, yes.
But I imagine that connection also leads to some pretty unique challenges, right? It can't all be straightforward.
Oh, definitely not. There are some major hurdles. One of the biggest is that very hardware dependency we just talked about.
Limited access, you mean?
Yeah, you often don't have enough of the final hardware, especially early on.
Yeah.
And the emulators or simulators you use instead, they're useful, but they might not perfectly mimic how the real thing behaves.
So they could give you a false sense of security?
Potentially, yes.
Yeah.
A false sense of performance or even usability.
Huh.
Another big one is the use of open source software.
How's that a challenge? Isn't open source good?
It can be, but many embedded projects use open source components that weren't developed in-house. And often, these components don't come with a complete set of tests from the original creators.
Ah, so you inherit code with maybe unknown quality levels.
Exactly, and it leads to this huge, potentially massive number of test combinations and scenarios the embedded team now has to cover.
Okay, that sounds tricky. What else?
Well, remember the parallel development issue. When you're building software for brand new hardware,
Yeah.
it becomes really hard to distinguish software versus hardware defects. You find a problem. Is it a bug in the code? Or is the brand new hardware itself faulty? Diagnosing that takes time and expertise,
I can see that. Pointing fingers, maybe.
sometimes. And then there's the problem of reproducible defects. Bugs in embedded systems can be notoriously difficult to make happen again reliably. They might depend on specific timing or temperature or some weird hardware state.
So catching it once is valuable, but you might struggle to analyze it.
Hugely valuable. Every time a defect shows up, you need to gather as much data as physically possible right then and there to try and figure out the root cause, because you might not get another chance easily.
Wow. Pressure's on.
And finally, these systems aren't static. They need continuous software updates. Maybe the underlying operating system needs an upgrade, security patches, new drivers for hardware,
Right. Always evolving.
which complicates finding bugs that might be introduced by those updates, and it really stresses the importance of having solid processes for building and deploying software updates safely. It's a constant cycle.
That's a lot to juggle.
Yeah, if you boil it down, the fundamental issue in embedded testing really circles back to that deep reliance on the hardware environment, which again is often being built alongside the software. Plus, you often need specialized, custom tools. It's complex.
Oh, okay. Those are some pretty significant hurdles. Hardware dependence, open source gaps, hardware versus software bugs, reproducibility, constant updates. So given all that complexity and the high stakes, what's the most effective path forward? What does the material suggest?
Well, the clearest recommendation, especially looking at all those challenges, is very often to lean heavily on automated software testing.
Automation. Makes sense.
Mm.
How does that help specifically?
It tackles several of those issues head on. It helps with hardware dependency through techniques like hardware in the loop or HIL testing, where automated scripts run tests on the actual hardware.
Okay.
It helps manage the complexity of open source components because you can create extensive, repeatable test suites that run automatically. It really helps with defect reproducibility by setting up controlled environments that can be reset and run again and again.
So you can try and trigger that tricky bug consistently.
Exactly. And it's absolutely crucial for handling those continuous updates. Automation tools can integrate right into your build and deployment pipelines, your CI/CD process, to test every change automatically.
So instead of a person manually clicking through thousands of scenarios, which is slow and error-prone,
Right.
you have machines doing it rapidly, consistently, exhaustively.
Precisely. Automated testing is just way faster. It can run thousands of tests in hours, not days or weeks. And it's incredibly effective at systematically finding and helping to resolve these complex software issues. For modern embedded systems, it's really the only practical way to scale the testing effort effectively.
What an incredible journey we've taken today, seriously. From defining this hidden world of embedded systems to understanding that really intricate 5-layer testing strategy, and then digging into the very real challenges testers face, and finally landing on the importance of automation. It really is this whole domain of engineering working silently, just beneath the surface of everything.
It truly is. And it's that rigor, that complexity of the testing we've been talking about that ultimately ensures the safety and reliability of so many devices we just take for granted every single day. They're the unsung heroes of modern tech, in a way.
Absolutely. So thinking about all this, what does it mean for you listening right now? Maybe consider a device you use every day. Something seemingly simple, your coffee maker, maybe a smart thermostat, perhaps your car's navigation. Knowing now about the complex, multi-layered, often automated testing that goes into its embedded software, how does that change how you think about it? Does it make you appreciate its smooth operation a bit more? And what other questions does it spark about all this unseen intelligence quietly working all around us?
CTSS